Hi, we're the Carleton Planetary Robotics team, and this is our submission for the University Rover Challenge 2024. CPRT was competing consistently in the competition up until 2019, when the team was halted due to COVID-19. Because of this hold, a lot of the knowledge from our team was lost, so one of the main focuses of this year has been developing a new knowledge base. To develop this knowledge base, we opted to do a ground-up redesign of our entire rover system this year. This includes a mechanical redesign, electrical, and code base. The team is mostly led by first and second years, in which we have over 100 active members who were recruited by our executive team this year.
Starting with the mechanical design of the rover this year, we've decided to move away from a full rocker bogie suspension to a hybrid one. This new design allows us to save weight on our suspension system while still maintaining 6 points of contact with the rough environment of the Utah desert. Starting at the base of our rover, our 3D printed wheels are connected to our suspension using a designed in-house slewing ring bearing. The wheels are 3D printed from TPU filament at 3 different infill densities. At lower densities, it allows for ductile shock absorption, and at higher infills, it is rigid enough to be mounted and still maintain its shape. This all-in-one wheel design has allowed us to integrate our tire, wheel, and hub into a single component, drastically reducing the overall weight of our drive system. Now moving up the rover, we have the arm. This year we decided to redesign the arm with two main goals in mind. First, we wanted to reduce the arm's overall weight, and second, we wanted to lower its center of gravity. We accomplished both these tasks by using a differential drive motor system at the base of the arm. Lastly, at the end of our arm is our end effector. Our end effector makes use of encompassing grip systems to allow for a wide range of capabilities. The fingers on the end effector are 3D printed and can be easily swapped out depending on the tasks being performed.
On the electrical side of things, our main focus is designing a power delivery system to step down the 22 volts from our LiPo battery to 12 volts for our motors and 5 volts for some of the sensors. To do that, we're using our custom designed power delivery stack, which is 2 PCBs on top of each other, one which takes the 22 volts, steps it down to 12, and the other one which steps down to 5 and delivers it to every other place in the rover. This will save space in the rover and reduce transmission losses through our high power sections.
This year's science team is the largest in CPRT history. With a complete redesign of how the science missions are approached, we've put hypothesis testing and the scientific method at the forefront of the team. To tackle this year's science mission, we've decided to break it down into 2 modules that will be on our rover, the Red Planet Scilab and the Molecular Analyzer. The Molecular Analyzer is equipped with a Raman spectrometer and a USB microscope. Using a mix of high-end spectroscopy equipment and custom-built components, the Raman spectrometer allows us to accurately detect extant and extinct life using metabolic byproducts like lactic acid and acetyl-CoA as our markers. Paired with our Raman is a USB microscope. This allows us to take microscopic pictures of the sediment, allowing us to do mineralogical analysis based on visual cues, such as color and angularity of the grains, and it will allow us to look for signs of extant or extinct life. The Red Planet Scilab is composed of a core extractor and of a subsurface environmental analysis probe. The sample is collected with a 3D printed core extractor. The core extractor has a one-way flap system which sequesters the sample and prevents the sediment from flowing downwards as the drill presses into the ground. This ensures that dirt from below 10 centimeters is separated from the dirt from above 10 centimeters, preventing cross-contamination. After extraction is complete, our sensor probe can be lowered into the hole that we just made. This will allow us to detect for CO2, temperature, and for total volatile organic compound. These readings will allow us to determine our sample site's ability to support and maintain life.
Due to having new members on the software team, we're approaching the software in a more modular and approachable way for new members. We're using ROS Humble as it allows us to build more modularly and test using different nodes, and it also allows for new members to be able to use Python or C++ depending on what they're more familiar with. For our navigation and autonomy suite, we're using a combination of LiDAR and stereo camera fusion. The stereo camera that we're using also has a IMU built in with GPS fusion enabled. We're using the NVIDIA Jetson AGX Orin as our main processor for the rover, which will take in the fused point cloud data and fused pose data from the IMU and the GPS to allow us to run the navigation stack to properly avoid obstacles. For our communications, we're using a 2.4 gigahertz antenna to communicate between the rover and the base station. This will allow for a theoretical output of 80 megabytes per second. That we're also implementing a custom RTK base station to allow us to get a positional accuracy of up to 5 centimeters at a polling rate of 10 hertz. Before the rover was even built, the software team was hard at work running on simulations. We've been working on arm simulations and autonomy simulations, allowing us to work concurrently with the mechanical team while they're physically creating the rover.
With a passionate membership base and fresh eyes for the competition, we hope this year is the year that we show everybody that we're ready to be a leading team again. Thank you.